Hi, my name is Dr. Sadie Jones and I work at the University of Southampton. My job is the Astronomy Public Engagement Leader, and I'm going to talk about a piece of research I did for my PhD between 2007 and 2011. I was looking at a particular black hole, the centre of a galaxy, because it was acting in a mysterious way. I'll give you an introduction to different types of black holes, specifically about the research that I did, and then I will point you to some further reading at the end. You will have all seen the electromagnetic spectrum in some form before, hopefully. You'll be very aware of the visible part of the spectrum because this is what our eyes detect. So we can see at a wavelength of 500 nanometers using our eyes, but space and the universe gives off light in all different parts of the spectrum, all the way from the radio, which is the really long wave radiation but very low energy, all the way to the gamma ray, which is very short wavelength radiation, very high energy. And as astronomers, we're trying to see the universe in all the different parts of the spectrum, and an interesting way to kind of examine whatever we're interested in is by maybe comparing different parts of the spectrum. For myself, I was comparing radio, which is low energy emission, with quite high energy emission from X-rays. Now, to observe X-rays, we have to put telescopes in space. So in this diagram you can see we have Chandra here, which is a telescope outside of our atmosphere in space. We have to put our X-ray telescopes into space because, thankfully for us, the X-ray and gamma ray radiation that would be very harmful to us humans is stopped by the atmosphere from getting through. So when you're trying to do optical astronomy, you use kind of standard telescopes, lenses and mirrors, and that's fine. And you can get very good what we call angular resolution. So angular resolution is basically kind of how much definition you can see. So you're probably all aware of high definition imagery on your phones and TVs. And if you think of this as just basically having lots and lots of pixels across the image, the more pixels you have across the image, the more detail you can see. So in astronomy, we want to have a very small angular resolution. For optical astronomy, we want it to be about maybe 0.01 arc seconds. Don't worry so much about the units here of arc seconds. Just know that we want it to be a small value, so like 0.01. So if your angular resolution is your wavelength divided by the diameter of your mirror, of your telescope, in this case we have a lens on our refractor telescope. So you have the wavelength, which is about 500 nanometers for optical telescope, divided by the diameter, which is about a few centimeters across. To get a small angular resolution in optical is quite easy because the wavelength is so small. So you don't need to worry so much about having a large diameter of your mirror or telescope. For optical, the angular resolution is already very small, just simply because your wavelength of the optical light is very small. So these days we don't use kind of lenses. We use large mirror telescopes with what we call a CCD camera on the actual back of the actual telescope to collect all those photons of light and make the image. And this is exactly the same technology that is in your smartphone. So we all take for granted that we can just point our kind of camera, or we can point our phone at something and take a very high resolution image. That technology, that CCD technology that you have, or we all have in our smartphones, was actually first invented by astronomers to take high resolution imagery. Or we must thank them for the ability to take such lovely photos of things. So this is a very high angular resolution image of our Milky Way galaxy, and you can see lots of detail here. The problem with this single image in optical is that there is a lot of gas and dust getting in the way of a lot of the light that is actually in the Milky Way. And this is because clouds of gas and dust, just like the clouds in the sky, they stop the optical light getting through. So it's just like the same reason you can't see stars on a cloudy night is the same reason we can't see a lot of the detail here, because of the material that's in the way. This is an image showing you the Milky Way in all the different parts of the electromagnetic spectrum. So you have the optical one, which I just showed you here, and like I can see that the center of the Milky Way galaxy is very bright, but you have all these kind of black features here, which is showing that the light can't get through. There's dust and gas in the way. And this is quite an interesting image on its own, but if you look in all the other parts of the spectrum, all the way up to radio, you'll see different features. So in the radio, the center of the galaxy is really bright, but you can see that you get radio emission from all the spiral arms and everything else as well. And then down here at higher energies, you have the center looking quite bright, but these features here are actually a lot brighter. And these are from kind of a supernova explosion that went off and is still giving out a lot of X-ray and gamma ray emission. Okay, so we know there is a supermassive black hole at the center of the Milky Way galaxy, and that is because we're able to track the actual orbits of stars going around this central object. Now, we know there's an object there because this is the center of mass, which these objects are orbiting around. But when we actually visually look into the center of our galaxy, at the location of Sagittarius A star, there is nothing there. We can't see anything. But the fact that these stars are moving around this central object with speeds tell us the mass of the thing they're orbiting around. So we can basically plug these values for kind of the mass of these stars and their speeds into one of Newton's equations, and the mass for the thing, the big mass that they're orbiting around, comes out as being 4 million times that of the sun. And the only thing that can be 4 million times that of the sun and be invisible and be in a very small volume of space is a supermassive black hole. So that is how we know. there is a supermassive black hole in our galaxy, and we call it Sagittarius A star simply because it is in the location of Sagittarius. So there are two different types of black holes. You've got the stellar mass black holes and then the supermassive black holes, which is the ones I studied for my PhD. The stellar mass black holes are as a result of the life cycle of a star, basically. You start off with material that collapses under gravity, it sticks together and forms a star. The star starts to fuse elements together, and when you have kind of a fusion engine inside your star, then a star is essentially born. Now, our sun is a G-type star, and it will not turn into a red supergiant. The red supergiant that most of you are probably aware of is Betelgeuse, which is in the Orion constellation, and you can see it's red even with your eyes. So when these big kind of supergiant stars come to the end of their lives, they throw off their outer the outer material in a big supernova explosion, which is so bright that is a similar brightness to the order of all the stars in a galaxy. So these are very, very bright events. And a certain type of supernova called a supernova type 1a is very interesting to people at the University of Southampton who study them, because they are a way of learning about distance scales in the universe, and will actually hopefully help us understand how dark energy is accelerating things in the universe. So if you'd like to know more about the research we do into supernova and dark energy, I will put some further reading articles on that on the blackboard. But for today, because I'm talking about my research, I'm mainly focusing on black holes. So when the actual supernova explodes, the central core, which will have been compacted under a lot of gravity, is incredibly dense. And if it can no longer hold itself up, then gravity wins over and the core collapses in on itself. So the core of that star that's left over after the explosion, if that is bigger than 3 times the mass of the sun, then it will become a black hole because it can't hold itself up any longer. If it is kind of less than that, maybe, I don't know, like 1, 2, then it will become something called a neutron star. So they're called stellar mass black holes simply because they're the order of the size of a few suns, And then we have the supermassive black holes, or active galactic nuclei, which is what I'm focusing on, also known as AGN. So this is a artist's impression. We are not able to kind of take an image in so much detail of an AGN at the moment, but this is what we suspect is happening. So you have the accretion disk, so you have material spinning around the supermassive black hole in a plane, and then at 90 degrees to this plane of the accretion disk, you have, for the AGN at least, you have this kind of jet. Now the jet is a bit of a mystery. We still don't really understand how jets work, how they can be anchored onto a rapidly rotating black hole, and how they can go out into space for so many light years and stay as a column. So they're very interesting, and that was kind of why I was doing my PhD research on them, because there are still so many questions that we don't know about AGN and the environment around the black hole itself. So just to summarize, we have the supermassive black holes, which exist at the centers of galaxies. We think every galaxy has a supermassive black hole in its center, and these are orders of millions of times the size of the sun. And then we have these binary black holes. So earlier I referred to them as stellar mass black holes, but they're also referred to as binary black holes because they're always with a companion. The only way we're able to see them is if they're ripping material off a nearby star, and it's that material that is getting kind of eaten up and therefore giving out radiation that allows us to see this accretion disk. These black holes in binary systems are usually about 10 times the size of the sun, but there are two different types within the binaries called low mass and high mass X-ray binaries. So these binary black holes are also extensively studied by people at the University of Southampton, and then we communicate with each other, the people working on the supermassive black holes and the smaller black holes, obviously having kind of conversations to see if there is features in both these different types of black holes that happen on different scales. So the research I did was on a supermassive black hole called NGC 4051. This is an active galactic nuclei, and it is interesting because it has behavior in both the X-ray and radio parts of the spectrum, which we wouldn't expect. So my supervisor had like an extra data set on it, basically, to see what mysterious, weird happenings were going on with this galaxy. So in the optical, it looks like this, and it can be seen in the region of sky which is very close to the Saucepan constellation, which you use to find the North Star. So if you're lucky enough to have quite a big telescope, you would be able to see NGC 4051 just in this location here. You might notice that it's labelled here as a Seyfert 1 AGN galaxy, and this is just a kind of a subtype of AGN, which I'll explain more later, but basically it just means that it's quite radio quiet, so you wouldn't expect to see a jet when you look with a radio telescope at this. You would just see some radio emission from the very center, where the material is kind of spiraling around magnetic fields near to the actual edge of the supermassive black hole. Okay, so this is a picture of another AGN called NGC 5128, which is 12 million light years away, and this is taken in optical. So this is what it looks like in optical. You could see the center of the galaxy is quite bright. You've got the spiral arms here, darker, and it is a nice image, but you don't really know all that's going on, all the inner workings, all the physics, until you look with different telescopes. Now we're looking in a different part of the spectrum. We have the optical, but we also have, we can also see X-ray emission here in blue, and some kind of radio emission here as well. So when you look with something like the Chandra telescope in space, it allows you to see this kind of X-ray emission, which is from the disk and the jet, and then you're also able to see this radio emission from the jet, where it hits what we call the interstellar medium. So the jets can kind of stream out as a column for a bit, but then if they hit lots of material they then kind of plume back on them, and we see these kind of features as what we call hotspots in our radio data. Okay, so this is a kind of diagram of what we think it looks like. Again, this is an artist's impression, but if you have the supermassive black hole here, then you have these magnetic fields, or B fields, which are, they're not just going straight up, they're spiraling, they're twisting as the black hole is actually spinning as well. So quite complicated, and it's like actually like a toroidal field. We don't really know how these magnetic fields kind of anchor on to this rapidly kind of rotating supermassive black hole. We don't know how they interact specifically well with the kind of edge of the accretion disk, which is exactly why we're doing this kind of research, to see if there is a relationship between the accretion disk, where material is kind of flowing towards the black hole, and then the jet itself. So what you might expect is, if you're doing an investigation like mine, is you get X-ray, an X-ray brightening, so like you get more radiation from the X-ray suddenly happening in the disk when material is kind of flowing forward, and then when it hits the edge, it doesn't fall into the black hole, it actually then gets accelerated around these magnetic fields, and at some later point would be very, very bright in the radio telescopes that are observing at a certain frequency. So if you can see kind of a flaring event here, and then several kind of days, minutes later, you might see a flaring event here, you can make an assumption that that there is a relationship between the two, in the sense that they are linked, that the material can flow from this one to this one, but also the time, because you know the speed of light, the time it takes for you to see the material flare in here and then flare in here, tells you things about the geometry and size of this whole system. The radiation that allows us to see this in the radio part of the spectrum is synchrotron radiation. So synchrotron radiation is basically wherever you get a magnetic field and you have an electron spiraling around the magnetic field, you will get synchrotron radiation. And so synchrotron radiation can happen in all parts of the galaxy, specifically where you might have star-forming regions, you get lots of synchrotron radiation, but you get obviously a lot of it here in a jet. So you would expect to see some radio. For my Seyfert 1 galaxy, I'm only expecting to see radio emission from this part very, very close to the black hole, where there would be some synchrotron. I'm not expecting to have a jet like this, so I wouldn't be expecting to see radio emission kind of far out from the core of the black hole. And I'm only really interested in the black hole region itself. So this diagram from a paper shows this effect a lot better. So if you're looking at 0 degrees, so directly down the jet, you would see a lot of radiation. You might see some kind of X-rays and stuff from what we call these narrow and broad line regions very close to the supermassive black hole, but you would mainly be seeing lots of radio emission because the jet just so happens to be directly pointing towards us here on the Earth. You have to remember that galaxies are not orientated all in the same kind of planes in space relative to us. They're all at different angles. So if you're looking kind of 90 degrees here, you're looking kind of through the accretion disk, and you might see just a bit of X-ray here, but you wouldn't be seeing basically any radio waves because you're exactly 90 degrees to any kind of jet radio emission here. So there's lots of different types. This is quite a confusing diagram, but the thing to mainly take away is that the AGN can be either radio quiet or radio loud. So the type that I am looking at is a Seyfert 1 galaxy, and we assume that we're looking at this galaxy from this kind of angle here. So we're looking through this kind of broad line region here. We get a little bit of narrow line region stuff, but we are able to kind of have a line of sight to the supermassive black hole. We might get a bit of radio emission from very, very close to the black hole in the core, and we would also get some X-ray emission from this accretion disk here. But we don't have a strong jet emission in this type of AGN, usually. So I was looking at it with something called the Rossi X-ray Timing Explorer, which is quite an old type of X-ray telescope, but it's simply just pointing at my galaxy for a few days and counting the amount of X-ray photons that come in and the energy of those X-ray photons. And then over time, I plot these X-rays on a graph, and you can see that when you smooth out the data, the brightness of the X-rays at the very center around the actual galaxy associated with the disk around the supermassive black hole, you see a brightening and then a dimming and then a brightening. And this is interesting on its own because its variability is quite fast, and that was what my supervisor was interested in. But for me, I was interested in the more kind of long-term variability pattern you see here, and then comparing it with the radio. So I needed to look at the galaxy at the exact same time, simultaneously, with a radio telescope. But the problem I have is that when you're doing radio astronomy, it's very different to X-ray, it's very different to optical. In optical, you just take an image of something and the image is right there. And you take for granted what's gone on inside your kind of smartphone to create that image. For radio astronomy, well, it's definitely not that simple. So first of all, thinking about angular resolution again, this is our angular resolution equation I showed us earlier. So now the wavelength of radio waves is much bigger. So this value here is 1 meter, not 500 nanometers. So because this number here is so big, to be able to get a really good angular resolution, remember we were trying to aim for something like 0.01 arc seconds, we need this value d, this diameter of our telescope, to be really, really, really big. And engineering would stipulate how big your radio dish can be, because if you try and make the dish too wide, end to end, the dish will just collapse on itself, and that will be good to no one. So what we use is something called interferometry, which means we can connect several big radio dishes together. So the diameter of your telescope, your radio telescope, is actually now the furthest distance between those dishes. So the radio interferometer that I had data from is called the VLA, which stands for Very Large Array. Very imaginative names in astronomy. And this is 27 kind of radio antenna all linked together with the internet, fiber optic cables underground. And essentially the diameter of my radio telescope when I use the VLA is the furthest distance in the two furthest apart antenna. So the A array is the best resolution. So what that means is when the antenna are as far apart as they can go. So these are all on train tracks, and the people move them along to get them farther apart. And when they're as far apart as they can go, they give you a diameter of your kind of array at 36 kilometers. When they're as close as they can be together, they have a diameter of 1 kilometers. So there's a big difference. And for my data, because I'm only interested in the core, I want to get really, really zoomed down into the actual center of the actual supermassive. I want to get really zoomed down into the center of the galaxy. I'm only interested in the little area around the core, around the actual black hole. So ideally for me, I would have the array being in A array, the best possible resolution for the whole of my observations. So this is the A array image that I made. So this actually took me about 6 months before this image came up on my screen, because radio astronomy is what we call a dark art. It is very hard, and that is because you have to correlate all the different signals that come in to all the different antennae. So all the different 27 antennae are all receiving radio waves from my active galactic nuclei. So the way that we analyze them as they come into the telescopes is very important. We don't want to introduce delays, which would mess up our data. All this data that comes in from the 27 telescopes has to be simultaneously brought together to be able to make an image. and you have to correlate that and get rid of all the data that isn't useful. So with radio astronomy, you can get lots of interference from things like aeroplanes, people on their phones especially, but also the electronics inside the actual radio dish can also cause interference. So this image isn't particularly exciting maybe for you to look at, but for me it was very exciting because it had these three very clear kind of blobs, or at least definitely two blobs, which have a very high contour level, which shows that they are real. There is really some radio emission coming from this area of space. Now, I was only actually expecting to see one blob, which is just the blob from the radio emission from stuff swirling around the black hole at the core. I wasn't expecting to see these two blobs here. So that is interesting. The fact they're symmetrical means that they could be a jet. Well, it could be evidence of a jet because they're symmetrical, and the fact this one is brighter, has more contours, means that the jet is kind of pointing, this jet is pointing towards us. Now, the whole jet thing is really interesting, but for now we'll put that aside and focus on the core radiation in the radio. So what I wanted to do is draw kind of a box around just the core. So I'm just getting the brightness on the core only and measure the brightness in that box. Okay, and all that brightness is what we call intrinsic to the supermassive black hole itself. And then I'll just do that for all my different images, and then I can make a light curve over time of seeing how the radio brightness changes over time for NGC 4051. So this is the light curve. So the top graph is showing you the brightness of that core over time. So you can see it gets brighter and then dimmer and brighter again. And if you remember the X-ray diagram, you will remember that is what happened for the X-rays. The X-rays from the core of the galaxy also got brighter and dimmer and brighter again. So just by comparing those two graphs side by side with my eyes, no fancy software, I can say there does look like there is a relationship between the radio and X-ray, and therefore there is a relationship between the radiation processes near the actual core of the black hole in this instance. So just down below the light curve, I just wanted to show you the difference between the two different array configurations. So in the best resolution configuration, you just see three blobs, which are kind of symmetrical, and those are associated with the black hole and this potential jet. When you look in the D array, which is much lower resolution, you're now seeing the center of the galaxy, but you're also seeing kind of emission. So you've got some synchrotron emission here from the spiral arms of the galaxy. So if I was interested in looking at the galaxy as a whole, or synchrotron in the spiral arms, I would want the VLA to be in D array all the time. I really wanted it to be in A array all the time. So I wanted these 5 green points here all in A array. Ideally, I would have had my radio telescope be in A array for the whole period of my observations. But unfortunately for me, the VLA was actually changing configuration during the time it was looking at 4051. So if I want to measure the brightness of the core in D array, I draw my box again, which I draw the box as small as I can get it, making sure that I get all the flux, all the brightness from the core in, but try and get as little as possible from the spiral arms. But even with your eyes, you can see that in D array, these contours are brighter, closer together at the very core than they are in the A array. So what you see here, where the D array, these are brighter than when the VLA is in the A array. So the problem I had is this brightening that we see here real? Is this intrinsic to the actual black hole and what's going on in the physics around the black hole? Or is it just to do with the fact that this image I've taken this value from is actually a much lower resolution image than when I'm looking in the A array, and I can see a lot more detail. So when I'm looking in the A array, I'm essentially zoomed in just on the black hole. So all this spiral arm features is there, but I'm just zoomed in on the black hole, so I don't see it because now it's really, really far out of the image. It's not kind of bleeding in this box that I've drawn. The problem is in a D array is essentially you have much bigger pixel sizes, so the pixel is bigger and a lot more of the flux is going to be inside here, and it's potentially going to be affecting my data. So even though I originally got quite excited by the idea that this light curve was following that of the X-ray light curve, what I realized is that I needed to remove some of the brightness contribution here that is actually due to the telescope, and it isn't actually due to the physics and the goings-on that is actually in the black hole, which is millions of miles away in space. So here you can see what I've done to subtract off the flux. So when I take off the brightness, which is due to the changing of the resolution of the array and not due to the black hole itself, I subtract it off and I end up with a new light curve, which is this one here. And now this kind of very strong variability where it goes up and down has totally disappeared. So these are varying between like 5 and 0, and this is now varying between 0 and 1. And there's quite big errors here, so I could essentially draw a line through this and there is no variability. So assuming that there's very little variability in the radio, it does now appear that there isn't such a strong relationship between the radio and an X-ray emission that I see in my galaxy 4051. But I can check this variability again by putting these two light curves through a piece of software called cross correlation function software, and seeing if there's any regions where a flaring event, for example here in the radio, corresponds to a flaring event of a similar size and scale to that in the X-ray. Originally I would have thought it would have been quite easy, because if this radio had gone up and down and then up again at the same time as the X-ray, then this would have shown a very kind of strong positive correlation with each other, and then we would have been able to say there is this strong relationship. But now after subtracting off this flux, which isn't real, which is just due to the telescope, you can see that the radio variability, which is from the very core of the black hole, isn't so strong as the X-ray variability. But this is just one galaxy which I've looked at, and lots of people have looked at a lot of other active galactic nuclei and stellar mass black holes, and what they've seen is that the X-ray and radio emission does follow or is lagging by a certain amount of days, and those amount of days that you see a flaring event happening in the disk and then maybe see the flare event happening a few days later in the jet tells you about the geometry of the black hole system, and tells you that there is this kind of potential strong relationship between these two types of radiation around the supermassive black hole. Now, I was very lucky that my supervisor was able to get access to something called very long baseline interferometry, and this is essentially taking radio antenna from across the world and connecting them all together. So now your diameter of your telescope is essentially the size of the world. Woohoo! And this gives you a very good resolution, very similar to that which you get for some optical telescopes. Now you have 0.02 arc-second resolution for the VLBI. So the idea was we look at this galaxy with VLBI, it will have even better resolution than our A array image from the VLA, and we'll be able to see if we do have these kind of jet images. So we're expecting hopefully to see 3 blobs again, very well defined. And this is what we got. So again, you might think this isn't very exciting, but we did have these 3 blobs here which are symmetrical. So this one, which is kind of the center of the image, is the supermassive black hole at the center of the galaxy. And the fact that you have these 2 features here, which is symmetrical, would suggest a jet. Now, what you do to make this contour map is that you read the level of the noise, which is here, the background noise, and then the contours represent either 1 or 2 or 3 times the size of the noise. So ideally in physics or science just in general, you want your value to be at least 3 times the background noise, so 3 sigma, to be able to be sure that it is real. So none of these values are 3 sigma, so it could all just be artifacts due to radio interference and things within the actual telescope. But the fact that they are symmetrical and they're 2 times the size of the noise is enough for me to be able to write a paper on this structure that we're seeing. And the fact that you see this kind of feature here where it looks like a hotspot, so you have the kind of shape of something hitting the interstellar medium and then kind of pluming backwards, is indicative that it could be a jet. Now, I said earlier that a Seyfert 1 galaxy isn't supposed to have a jet, but what we've learnt from looking at the kind of low mass and high mass X-ray binaries is that throughout a kind of black hole's life, you might get the jet turning on and off. So what we could be seeing is like a relic of an old jet that used to be quite active, that isn't obviously anymore, but you're still getting some synchrotron radiation from this region here. So ideally these contour levels would have been at least 3 times the level of the background noise to be sure that all these features are real. But that is not the case, unfortunately. So this is just one investigation on one AGN, but obviously lots of other people have done investigations very similarly in X-ray and radio to see if there is a relationship. All the data from all the different people who've done similar investigations to me can be plotted on something called the fundamental plane of black holes. So we're plotting radio brightness against X-ray brightness and scaling for the mass of the supermassive black hole. So my galaxy here, 4051, is represented by these triangles. So if you average all those triangles together, you get a spot here. Now I have been quite naughty and I haven't put the error bars on any of these values, but all these little specks here are basically other people who've done analysis of either the small binary black holes or kind of larger AGN and quasars and blazars. And you can see when you put them all on the graph, you plot their radio and X-ray brightness, that that you are able to draw a straight line through them, which is great. Scientists love drawing straight lines through data points. And this means that, well, that there is this strong relationship between the radio and X-ray brightness for black holes. And that is why we call it the fundamental plane of black holes. And it's important because you could basically, knowing the radio brightness of something, you could draw a line along here and then measure off the X-ray and estimate also the mass of the black hole. And estimating the mass of black holes is really hard. You could do something called reverberation mapping, where you're looking at the speed of material kind of swirling around the center of the galaxy or around the black hole region. But it is really hard and it has lots of errors in it. So any other ways that we can find of estimating the black hole mass is really positive. The other thing I should say about this diagram is you have this big IMBH here, which stands for intermediate mass black holes. Now these are a bit of a mystery. Why do you have lots of black holes which are like 10 times the size of the sun? And then you have lots of black holes which are millions of times the size of the sun. But why do you not have any black holes which are like, I don't know, 100? 1,000? We don't know why in physics, because we don't know why. So we would have thought they are physically possible. There's no real reason why you shouldn't be able to get a black hole that size. So why is there a gap in this data? Why are we not able to see these intermediate mass black holes when we look with our X-ray and our radio telescopes? That is a mystery that a lot of people are trying to figure out. But we, at the University of Southampton at least, we're trying to look at both the kind of large AGN and also the smaller binary systems and see if there's relationships like this one which are happening in both. And then by looking at the smaller black holes, which live kind of shorter lifetimes and we can see within our Milky Way, we can then infer relationships in these big black holes. So in 2019 on the news, it was very exciting. There was this image that was all over the place, which is the first image of a black hole. Now you might think, what is she on about? Because she just has been showing us images of black holes for this whole talk. Now I was showing you the core, so radio emission from the core of where we think there's a black hole, but it didn't actually have the black hole itself. Okay, because it didn't have such a level of angular resolution that I was able to resolve the fact that there was a hole in the middle. It was just a blob where you see this radio emission coming from around a black hole. So this is important, even though this just looks like a very orangey, blurry blob. The fact that there is a gap or a hole in the middle of this image is actually showing you the black hole. This is not just an artifact. This data had very good sigma. So this is why this is important, because this is actually an image of a black hole. We can resolve this hole in the middle of this radiation here. So this is an image of M87, which is a very, very active galaxy. It has a very, very powerful jet, very well looked at in X-ray, but this is the first time, obviously, that we've looked at it in such high angular resolution in radio waves. So this was very, very exciting for me, especially because I understand how hard radio astronomy really is and how exciting it must have been to see an image like this coming up on your computer and being sure that this isn't an artifact and this is actually real and this is a black hole that you're seeing with your eyes. So just like the VLBI, the Event Horizon Telescope, which took this image, is actually a large array of lots of different radio dishes, but they're connected by fiber optic cables on the internet under the ground, so that they're able to correlate all the data from these different antennae in real time and obviously bring them together very accurately so that you're able to get this amazing image. When you look at the M87 galaxy, you zoom out a little bit, you're not just looking on the black hole. If you look at it with an X-ray telescope like Chandra, you can see that there is a lot more going on than just a simple kind of jet system. So the jet is coming out here, you have the kind of black hole image here from the radio, but the jet is actually kind of swirling around, it's hitting all this interstellar medium as the whole system is kind of spinning. So it's really, really cool that we've now been able to compare the Event Horizon telescope data in the radio to this X-ray data from Chandra and see that there's this really kind of extreme system going on in M87. So Katie Bowman led this breakthrough, basically. She made this possible with her and her team. So she's actually works in MIT and she's kind of a computer scientist, and she kind of developed the software that was able to bring all the information from all these different antennae together in real time so that they were able to get such a high angular resolution image of M87. So it's really amazing stuff. If you would like to know more about this research I've talked about, I will post some papers on both AGN and supernova on Blackboard in the physics section. So thank you for listening to this webinar, and if you would like to follow me on Twitter and Instagram, go to @SartanAstrodome.